The next thing we want to discuss is the law of exponents that applies to the generalized exponential function. In the previous discussion, when we discussed the exponential function, we have seen theorem 3, where theorem 3 is a set of 4 rules that applies to the exponential function e power x. The generalized exponential function also follow a set of theorems similar to that applies to the exponential function. The first rule that applies to the generalized exponential function is a power x1 times a power x2 equals to a raised to the power of x1 plus x2. Second theorem is a power minus x equals to 1 over a power x. The third of this is a raised to the power of x1 divided by a raised to the power of x2 is just a raised to the power of x1 minus x2. The fourth theorem is a raised to the power of x1 is the same as a raised to the power of x2 raised to the power of x1 equals to a raised to the power of x1 times x2. I have to make some corrections to this point x2. You can prove these theorems one by one. However, we will only show you how the first and the second is proven. You have to prove that the product of the exponential function with x1 and the generalized exponential function with x2 is the same as the generalized exponential function raised to the power of the sum of x1 and x2. To do this, we have to resort to the definitions of the generalized exponential function expressed in terms of the exponential function. Namely, a power x is e raised to the power of x times ln a. Here we have to introduce two generalized exponential function, one for x1 and the other for x2. I'll call this y1 and I'll call this y2. I then multiply y1 with y2. That equals to e power x1 ln a multiplied with e x2 ln a. And according to the power law that applies to the exponential function, u multiplied with v, that is equals to e of u plus v. So here we will write down the product of the two exponential term as e raised to the power of ln a with x1 plus x2. After that, I'm going to take the log on both sides of this equation. The log of y1, y2 is then equals to the logarithm of the exponents of ln a x1 plus x2. And this right hand side term is simply equals to ln a times x1 plus x2. This is written down by understanding that the log of the exponents of anything is just equals to that anything. The anything that I mentioned here, represented by the star, is the log a times x1 plus x2. I then slot in the expression of a power x1 for y1, a power x2 for y2. Then I arrive at this equation. The next thing is to take the exponential again on both sides of the equation. When I take the exponents on the left hand side of this equation, I get a power x1, a power x2. When I take the exponents on the right hand side, I have this ln a multiplied with x1 plus x2. The right hand side here is in the form of e to the power of x1 plus x2 ln a. And what this is nothing but just a to the power of x1 plus x2. The product of a to the power of x1 and a to the power of x2 is simply equals to the a raised to the power of x1 plus x2. Let us try to see how we prove the next theorem, that is a raised to the power of minus x is equals to 1 over a power of x. We are going to prove these statements in an informal manner. What I'm going to do is I'm going to look at the left-hand side and try to take the log of the left-hand side. Then I'm going to take the log of the right-hand side. Then I'm going to compare the final expression of the log of the left-hand side and the log of the right-hand side. After comparing, I'll be able to conclude that indeed the log of the left-hand side is the log of the right-hand side. Therefore, the left-hand side is equal to the right-hand side. Let us look at the left-hand side. Left-hand side is a to the power of minus x, and I'm going to take the log of it. The log of it has to be taken by converting the generalized exponential function into exponential function, which is minus x ln a. Then I'm going to look at the right hand side, and I'm going to take the log of the right hand side. The log of the right hand side is just equal to the log of 1 minus log of ax, because log of a over b is the difference of the log of a and log of b. Here we take the a to be 1 and the b to be just the a to the power of x. This is nothing but just negative of the log of ax. I'm going to express ax in terms of the natural log, which is e to the power of x ln a, and this negative sign is crucial. It comes from here. I'm going to raise the negative term into the log, and this is just equal to the log of e power of minus x ln a. So up to this point, I have already shown that the log of the left hand side ends up to be like this, and the log of the right hand side ends up to be like this. So you can compare the log of the right hand side and the log of the left hand side. So you find that this and this are exactly the same. So what I can conclude is that the log of a power minus x and the log of 1 over a power x, they are equal to each other. Therefore, I conclude that the arguments inside the log must be the same. And that is the proof of this theorem. Let us look at example 3 that involve the evaluations of the numerical value of general exponential function. The first part in example 3 requires you to calculate the values of the 2 raised to the power of 3. This is in the form of a power x. Here a must be a real positive number, which is 2. X is just the square root of 3. According to the definitions of the generalized exponential function, a power x is evaluated to be e raised to the power of x times ln a. So what you need to know is that you have to first calculate what is the log of a. Then you calculate what is the square root of 3. Multiply them together, you obtain the values of square root of 3 times the log of a, which is 2 in this case. Then you have to take the exponents of the value square root of 3 and 2. This is the way how you do that. First, you go to the root of alpha. You have to first calculate the values of log of n, which is 0.63. Then you have to multiply log of n by square root of 3. So that gives you the values of the log of 2 times square root of 3, which is 1.2. After that, you have to then equate the values of the exponential function evaluated at square root of 3 times log of 2. So this will correctly interpret the numerical value for 2 power square root of 3, and you get a number which is 3.32. Mind you, the values of 2 raised to the power of square root of 3 is not calculated by any magic. It is calculated through this step-by-step procedure, where you first define what is log 2, then you calculate the square root of 3, then only you calculate the exponential of the argument inside the exponential function. In part B of the example 3, we have 2 raised to the power of pi. So this is to be identified as a power x. So again, a plays the role of a base, which is 2. Then here x plays the role of pi, which is an irrational number. To calculate the value of 2 raised to pi, the correct way to evaluate the numerical value is the value of the exponential function with the argument of x ln a. X is pi, ln a is just ln 2. So again, to calculate the values of 2 power pi, you ask the Wolfram alpha to do it for you. You begin by calculating the values of the natural log of 2, multiply with the values of pi. So that is the values of the natural log 2 multiplied with pi, it gives you this number. Then you slot in the values of the log of 2 times pi into the exponential function. Then Wolfram alpha will interpret it correctly to be this, and then you find that it actually gives you the exact result of 2 power pi, and the values is 8.82 as shown in the screen. The number given to you here by the Wolfram alpha is by first calculating the log of 2 multiplied with pi. After they have obtained this value, then calculate the exponential of this value to represent values of 2 raised to the power of pi. This is how the generalized exponential function is calculated numerically. As a conclusion to this video, we have discussed how the generalized exponential function is defined based on exponential function. We have also discussed the laws that governs some of the property of the generalized exponential function. We have also discussed a few examples of how to numerically evaluate the generalized exponential function based on the values obtained from the exponential function according to the definition.